Hello, everyone. Welcome to the sixth episode of Gradient Descent, where we try to dive deep into a specific topic in AI. And my name is Vishnu. I'm the founder of Wisecube, and I have here with me my co-host Alex Thomas, who's a principal data scientist. Hi, Alex. How are you doing this
Hello.
week?
I'm doing pretty good. How about yourself?
Doing good. It's summer's officially started in Seattle, so the sun's out, so that's always good. Like where you live, the sun's always out, right?
I'm in Florida, and summer is sort of like when you start getting the afternoon storms. So.
Oh, yeah, that sounds. Well, I don't know. How does that? How is
It's
that?
like the if you've ever seen like Doctor Who with like the Master and the drum beats, sort of warning of the upcoming hurricane season.
Oh my god, that sounds ominous.
These big black clouds come in every afternoon, thunder.
Nice. Yeah, this is why I don't live in Florida. But then again, a lot of people do. So they clearly like something about it. I grew up in India, so like when I go to Florida, it reminds me of I grew up and it's very hot and humid. And anyway, well, let's get back to the episode. Like this week, we do have some news to announce. So some of you might have already seen it. Like Wisecube is the company that we started like almost 8.5 years ago. Sort of reached a point where we decided to become part of a company that we've admired called John Snow Labs. So that acquisition sort of went through, and so now we're part of the John Snow Labs family, who also are doing some really great work with NLP, and we have some great connections there, and we thought it'll be a good time to not only recap our journey to this point, and that ended in this sort of the exit of Wisecube becoming part of John Snow, but also just taking time to recap the story so far as far as NLP and AI is concerned, and sort of share some personal stories along the way. Was the hope. So so that's going to be today's episodes. It's just a recap. So Alex, you were talking about this episode from Community, where there's a recap show where they don't really recap it. I don't think we have enough episodes to recap all the episodes in Gradient Descent, but we're gonna recap something completely different. But yeah.
So I think it's in the second season, if I recall correctly, and basically they have a bunch of flashbacks to episodes that didn't occur. It was it's sort of like a fun take of doing sort of like this old trope of the recap flashback episode. But yeah, in their case, like you said, we're too new to really have much, but we've both been working for a while, and so there's and sort of the thought for this episode was like we could talk about a little bit the history of NLP that leads up to where we are with LLMs. And it sort of parallels to some degree our work history. We began very early on working on a lot of like search engine stuff, and that's similar to a lot of foundational things in NLP.
So I'll cue the music with the going back in the flashback.
Yeah.
The spirals. Yes. That's how we got started, right? Like the whole you and I, for those of you who may not know this, we got started into this whole AI and NLP space almost. I want to say, for me, it was 15 years ago. I think for you, it was like 13. Okay, so 15 years ago, Seattle, it was Bellevue actually. This company called Pythia, never heard of it, and I was like, oh, we're doing search, NLP and machine learning and all that, and I was like, whatever. So they were essentially a search engine company. Well, they were not building search engines, but they were like a search company.
Yeah.
They were focused on traditional search, search-based products. They had this technology called X relevance and X patterns. That how would you describe X relevance and X patterns in the most marketing friendly way?
So sort of relying a little bit on the history I know that coming before I joined, is that there was sort of like a data, information extraction stuff that became sort of like advertising recommendation, and the sort of models built around doing that were supposed to be like a learn to rank search engine that uses a neural network to learn from the clicks.
I think the biggest innovation I would say is like what they were trying to do was this idea of what the founder described as a DE or domain expert. So the idea was like you could have your general corpus, and then you could search through your general corpus, which is pretty much what everybody did with search engines back then, right? They throw it into like Elasticsearch was not a thing back then. So it was like Solr or basically Lucene Index.
Yeah.
And then you would run your search. The problem with doing that, of course, is the relevance is not going to be that great. It's going to do basic TF-IDF, right? And so that will give you some, it's not bad, but then it's not going to be very domain specific, and so it's just going to look at counting like your term frequencies and your compared to your document frequencies and all of that, and then start ranking that. And so your Ranko is pretty generic, right? And so the whole sort of innovation behind this new search product that they came up with was like, hey, what if we can actually build a separate specialized sort of index that's more domain specific, that has some of these terms and terminologies, almost like a knowledge graph, but not a knowledge graph. They were trying to build like an index of all of these sort of terminologies that are much more relevant to the domain itself. And then they would use this specialized corpus that they call the domain expert as a way to do query expansion.
Yeah.
Right. And that was one of their sort of key sort of innovations, which is like, hey, instead of just searching for, I don't know, this is the classic example they'd always say in the healthcare space. People were like, oh, if I search for heart attack, I'm gonna get all the documents that rank for heart attack. Great. But as a domain expert in the field, as a medical professional, heart attack is also referred to in the literature as, myocardial infarction, for example. Yeah. So that is not even going to show up in your search results. And that will be bad, because you're like, what? What about all the articles that talk about myocardial infarction? And so the way to, and then they would, that's how they would fix this. So they would actually, before running just the results of the query themselves, they would take the original query, run it through this DE or this domain expert corpus, and then they would get related terms. Yeah. And they say, oh, it'll show up with like myocardial infarction and all the other terms that are related to heart attack.
Yeah, there's a couple terms. Couple terms you've used that I sort of want to unpack for some of our, because I think now a lot of people are coming into data science and NLP basically like purely through LLMs or maybe just like a little bit of deep learning stuff. So TF-IDF stands for term frequency dot inverse document frequency. And basically it's a way of like combining like a global feature with a local feature for the document. So the idea is like if I search for that will have a high term frequency in any document, but the idea is that its document frequency is also going to be really high. So if you have the inverse of that, that'll sort of like shrink the value of so that will dominate your search. Meanwhile, if I'm searching for myocardial infarction, myocardial is a relatively rare word in the corpus. So if it occurs a lot in the document, that will be the thing that influences it to be returned. The other thing you mentioned, disambiguation. I'd say like sort of what the DE was doing was not necessarily in a bad way, was trying to ambiguate, because this is an era before word vectors, right? We didn't really have those at this time, and you could sort of do it with non-negative matrix factorization. You can kind of do word vectors, but like it wasn't as easy as what we have now with like semantic search in order to solve the problem you're talking about. So this was like a difficult problem at that time. Yeah,
and so by doing this sort of query expansion, what they were trying to improve upon was the recall, right? For those of you who know precision recall, so there's two sides, of what you want to try to improve. You would improve the recall because now you're including documents that otherwise would not get included in your original search query, and your recall gets better. But for those of you who know this, there's no free lunch, and so when you improve your recall, your precision will take a hit. And so the way they sort of wanted to solve that is that this is where like what Alex was alluding to earlier, which is like, oh, we're going to train a ranker, or using a deep learning model, or actually there was no deep learning back then. It was just a neural network model that we would then try to build a better ranker than just using a TF-IDF out of the box, and then it would learn from what the users are actually doing when they're selecting the results. And so it would be like, an intelligent ranker that would learn from the user feedback as they're starting to use the product. And then it would get more and more intelligent, right? And so that was the idea, is like how we're going to solve the hit to the precision. Now, the problem with that approach is if you're going to depend on user usage of your product to improve your precision and just focus on recall, there's a thing in machine learning, as you probably all know, is the cold start problem.
Yeah.
That is going to be hard to solve. And so that's where we, at least this whole methodology sort of ran into trouble. It was like, it had a huge cold start problem. Right. And we would do these projects where we take huge corpuses and we would index them. We would build the DE. The recall would be great. The precision would not be that great. And then we're showing these demos, and they were like, "Well, hey, this is a whole bunch of stuff is showing up, but the topmost results are not what you would normally want to show up." Right. And so the rankers were not doing that great of a job out of the box, because it was just TF-IDF most of the time, because the neural network model was not trained, because there was not enough input to actually train the model to make it even more precise.
And I think this sort of goes into like another thing, like these search features, TF-IDF, are, I would say, were, and probably a lot of companies still are, commonly used features for document classification. It's called a bag of words. And it's sort of basically for every word in the document, you're going to have a TF-IDF score with it. And that sort of creates like a document, a very sparse document vector. And when I joined Ategio, we were working on this project. It was a search project, but like we were trying to find cohorts for trials. It was a text retrieval and evaluation conference. And it was basically this task of, hey, we're going to give you sort of like this short description of the type of people you want for a trial, and you're supposed to find the correct documents from a list of like 100,000 anonymized like hospital notes. And yeah, so we were trying to do use X patterns for this, and it wasn't really working. And I think that what we did end up doing that helped us do pretty well in the conference is we built something that essentially filtered down the vocabulary to just the medical vocabulary, because that problem is with precision and recall. If you are trying to like expand your search on the query coming in, like there's going to be words that are not as relevant medically, and if you try and expand on those, you're going to really muddy the water, even if your corpus is just medical. And so by like filtering everything down pretty aggressively to just medical terms, helped us do well, and then that helped us with our next project, which was CAC.
That's right. And so one of the ways the company at least pivoted to sort of become more specialized in some of these and solve some of these cold start problems is we started pivoting into a specific vertical. In this case, it was healthcare, and so we can actually start training some out of the box models to help with this problem. And I mean, not so much in search, but specifically like CAC is the product that Alex called it. For those of you who don't know, it's computer aided coding, and it's not coding as in like programming. It's medical billing. So a little bit of a background here. Any of us who've gone to at least in the United States, if you go to a provider of a doctor or physician of any kind, and there's usually an insurance company involved that you're on a plan for, and then once your procedure is performed, even if it's an office visit, in order for the provider, in this case the doctor, to get actually paid for the services they rendered, they have to define the services in this sort of coding terminology that's been internationally defined, called ICD, or in this case procedure code. So there's a medical billing code that's associated with any kind of procedure that any doctor can perform, and there's different categories of them, and there's different codes and subcategories, and there's a whole list that's published by who publishes these, Alex? I don't know which body. There's an international body that publishes this. Yeah,
I don't remember.
Yeah, we'll look it up and post it on the show notes. But and so unless you provide the actual exact medical billing code that's defined by ICD and CPT and all of these things, to your insurance to the insurance provider, the provider does not get paid. And so what would happen is after the procedure's been done, whether it be office visit, the physician would dictate the notes of like what was done, what was the patient, and things like that into a voice recorder of some sort, and that recording would get transcribed overnight by some call center or somewhere else outside of the U.S. typically, and the transcription would come back, and then they would take the transcription, and then they would be either in-house a person who can take the transcribed recording notes and then associate based on the procedure that was performed and the condition. They would attach these medical billing codes and then submit a form to the insurance company saying, hey, this kind of procedure is performed for this patient, and here's the billing codes. And once they submit that, there's actually an intermediary that would then submit it to the insurance company, and then that's sort of how the doctor itself would get paid for the services they performed. Anyway, and so as you can imagine, this process of actually attaching billing codes to, from unstructured transcription notes that the doctor provided is, it's a pretty manual, semi-manual process. And so this system that we were developing was, we were trying to automate the most, if not, that process to help the medical billing coder. And so it was like a co-pilot for medical billing coders. Right.
And for like machine learning people, it's sort of a classic multi-label classification problem. But in terms of like the UX we presented it more like a recommendation thing, and that sort of ties into like another interesting topic, which I think is really relevant nowadays. Is so when we were building the models, like we would get, I'll just sort of use accuracy because I vaguely remember those numbers. We get accuracies depending on the codes of like 75 to 85%, which we were pretty happy with. But then when we deployed the system and we looked how often that the coders would be, oh yeah, that's a good recommendation, we were getting 95 and above % accuracy. And that sort of ties into this concept of the Eliza effect, which is where users of computer systems will project knowledge or human level understanding, human attributes onto systems. So these coders are like, the system recommended these codes, and we had justifications that we would highlight the text features that were relevant, and so that they tended to agree with it. So we were actually getting higher accuracy, and now of course that's sort of a thing that comes up again with a lot of like LLMs, where this is the danger of hallucinations. Like people will see these like hallucinations, and if they're not astute with working with chatbots, they'll tend to believe them, or at least that's the concern. And yes, sort of tying this back into like the history of NLP. So we have like sort of this search-based stuff. We have document classification, all sort of like classic use cases in NLP, and then sort of like deep learning hit. So that's just sort of like at the end of the TGO period, and shortly before you started Wisecube.
That's right. By the way, I just looked it up. ICD WHO published ICD.
Yeah. We should have guessed that.
Yeah, I guess so. Well, now that their funding is going to get cut a lot, so it's not going to. There probably won't be an ICD 11 or 12. I'm just kidding. But by the way, every version of ICD, which stands for the International, Classification of Diseases. So basically, it's a list of all known diseases and disease categories. To like as of now, like the human scientific, medical science at least. And so every year, as you can imagine, the list would get bigger and more complex and more categories, and sometimes reorganizing these categories. And so it's a very deeply nested hierarchical structure of all known human diseases and disease categories. And so when you're trying to train a machine learning system that can take unstructured text from a physician's notes and then turn them into like ICD codes, you can imagine this. It's a complicated classification problem, and so anyway.
And it's like a person with like somewhat of a linguistics background coming into it. It seemed obvious like if you take like the bag of words approach, you're gonna have a really hard time, especially with ICD-10 and later, where they pull a lot more detail. I think there's like a 10-fold increase in the number of codes between ICD-9 and ICD-10.
That's right. That's right.
And so basically, like the sort of industry standard way of document classification that was done, think like before 2015, was like bag of words, where you sort of lost all the structure. And it was pretty obvious that there's no way to really do it. And I think a lot of companies had these sort of difficulties. And deep learning came along, and especially once you get to the point where you have BERT, where you can actually capture the structural information in a way that's usable to an understood model like neural networks.
Yeah,
you really saw sort of like this jump in some of these capabilities.
On that note, so yes, you brought the point. That's sort of around the timeline where we started Wisecube, and one of the first projects that at least you started working on was the drug discovery problem.
Yeah.
Right? We worked with IDRI, it was an infectious disease research institute based out of Seattle. We did a pilot for them. They were researching tuberculosis, and what they were trying to figure out was like, hey, what the TB, by the way, it still exists. It's still a big problem, and there's actually, of course, there's medicines, but like these antibiotics that people give, but there's also new strains of TB that are resistant to antibiotics, and so there's always this sort of constant cat and mouse game that's being played by with the bacteria and and the things that come out, the antibiotics, and so they were trying to come up with new formulations of potential drug candidates that can sort of deal with these new strains of TB, and so that's the research problem they were working on, and so there's in drug discovery background. Yes, you go through all these different phases. The initial phase is like there's always like, hey, looking at like the mechanism of the problem itself and like with the biology and all of this, and then saying, okay, this is what we want to target, and then trying to come up with potential candidate drugs or compounds or small molecules in this case. That could be potential things, but then you need to first make sure that this new compound can actually have an effect. And then this was in the discovery world, it's known as QSAR, right? And so QSAR, which stands for like activity response, qualitative structure activity relationship. Basically, it's a way to predict the biological activity that a particular chemical structure can have. And so that was sort of the problem that we got brought in to sort of help with using machine learning techniques and deep learning techniques. So at this point, deep learning is there. We do have BERT-like models, right? And so there's a step forward in terms of where the industry has gone, to Alex's point, right? Like now we have neural networks and deep learning networks, not LLMs yet. This is pre-LLM, but we do have these embeddings that we can create from strings and text. We don't have to rely on just bag of words anymore.
Yeah.
Right.
And NLP techniques. Like another thing that sort of is relevant here is like once we started developing these ways of capturing structure, there began to be like certain ability to like take these approaches used for language and use for other things. It's already sort of was known in genetics for a long time that a lot of NLP techniques work well with genetics. But with chemistry as well, like depending on your representation of the structure, you can actually use some similar techniques. Like there were people who built transformer-based models, or rather, I would say like RNN. I should probably. I don't know if they did transformers, but like recurrent neural network models on a type of string that's used to represent chemicals called a SMILES string. It's basically where you sort of encode like the structure. It's a little bit lossy. I think you lose what's it called, chirality or something like that. You lose some information on it, but you mostly keep the information there. And we were primarily using that to try and predict early on. And then like two interesting things we learned from that. One is that they have these sets of small molecules that they have run assays on, and then so you can try and like train a model on that, and then do some in silico, in software, estimations for new chemicals before you try them in actuality.
Yeah, and just a little background there. So in silico, so in drug discovery, there's these various phases that typically like a drug has to go through. Not even a drug, like a potential candidate has to go through before it can become a full-fledged drug and go through clinical trials and get FDA approval and stuff. And before you go there, it starts out saying like, hey, let's understand the biology. And then once the biology is fully understood and where you want to target, then you look at like, okay, what are the chemical, like in most cases, when we're talking about a drug, it's usually a small molecule. And there's actually a definition of what a small molecule is, but the technical but it's like, hey, anything that has a molecular weight of less than whatever, and is considered a small molecule. And 90% of all the pharma drugs out there are small molecules, right? And so what Alex is talking about is taking the structure of that chemical compound and turning it into a string. Is this what's called a smile string, and that's a sort of a lossy representation of a three-dimensional compound, but a small molecule, it's a small one, right? And then so typically you go through the process of trying out if there's any kind of biological activity on a new structure, whatever you're trying to improve, or not. In this case, you're trying to inhibit the growth of the bacteria in TB. You would run like through in vitro tests, which is like you'll create a version of that small molecule, and then you would put it in a test tube, and you would grow like the TB virus, and then you would see if it actually inhibits the growth of the TB bacteria, and then you would see if it inhibits the growth of the thing, right? Now, of course, as you can imagine, that takes time in order to like come up with hundreds and thousands of structures that you want to test out. Now there are high throughput testings that then there's automation in the labs, and you can sort of do that, but it still takes more time than it would take to do everything in a computer, right? Where you can just simulate. If you have an effective enough model that can predict the activity that your compound can have on the TB bacteria, then you would like almost pre-screen all of these new structures that you're trying to test in the computer, using this sort of model, which they didn't have. Like their out-of-the-box model they were using was not very good. It was basically random. And so they came to us and said, hey, can you build a better model that can act as an effective screen before we run it through like the high throughput screening system and have actually test it out in the lab, right?
And
at this point, go ahead.
And this is the thing we ran into, which is a generalization problem. So they had so these collection of molecules that they have done assays on. They call them libraries, and so they had two libraries available, like a sort of openly available one, and as well as a proprietary one. And what we found was that if you built a model on library A, it was nearly random on library B, and lots of reasons I can explain that. Like they're probably like the chemicals that make up those libraries are probably selected very differently. So, there's probably a very distribution of the relationship between these structural features and the relationship, or the inhibition relationship. And so that's sort of like led us to this idea of, I think Vishnu, you were the one who I think originally came up, found the paper for it, of like we could use a knowledge graph, build embeddings, and we could learn a much more like general sort of foundational model. I think it's sort of like that's the term we're using now. Foundational model that would get us past this cold start problem, right? Because like if you're testing these new molecules, if your selection pattern is like very different than the model you're using from whatever software you're getting, it won't work. So we need something to solve the cold start problem. And so we started working on the Orpheus project and building this really big biomedical knowledge graph. And this is like shortly after we began that is sort of like when like LLMs came out.
Also, there's a other historic event that happened in this process. COVID hit.
Yes.
And so we said, oh, you know what we should do is we should look at all the research that's coming out for COVID, because I don't know if you remember during that COVID time, the bar for what constituted a research paper like severely dropped.
Yes.
And there was this crazy amount of research that was published, and like most of it was like obviously not peer reviewed, but because there was such an inherent need for like any research, any clues of what could help. There's all kinds of papers, and people couldn't keep track of any of this anymore, and said, hey, what if we took all the research papers, we sort of index them, but also try to extract, try to build a knowledge graph of all the papers that are out there, and so so that's
anyway, right? Where it was just like entities and sort of their relationships as far as like how they were co-referenced. So like a very like basic knowledge graph. And we had a partner we were working with at that time who had COVID-related QSAR data.
Mm-hmm.
And what we found is that our very sort of like simple knowledge graph that was very general performed better at predicting relationships than the model trained on that data. So we were able to show that like our very big, very general, but also simplistic knowledge graph, because of its generalizability, performed better on predicting these new relationships.
Yeah,
and then we
and just to clarify, so in this case, what we would do is, like, because we had built this knowledge graph and going back to the embeddings like BERT, we had like an equivalent embedding model that we create using from the knowledge graph that we would train on all these entities. And so this was more like a network embedding that we trained on the entire graph. So for those of you who know BERT, so BERT just, tries to find like a high dimensional representation of all of the words, right? Like in your language or whatever. And then that's how you get to compare words and how semantically close they are, right? And so it's the same idea, but instead of it being just like text representations, it was basically related to the network representations of where an entity is in relation to other entities, what kinds of relationships do they have with other entities. That would go into computing the high dimensional representation or the embedding vector for each entity. I don't know, Alex, you want to talk more about that, how we actually trained the embedding model for the network, the network itself. Yeah.
And so similar to how word embedding, so like BERT and Word2Vec work on capturing sort of like the statistics around where the word appears, with the difference with Word2Vec being static and BERT being contextual. But they work on this on language structure, on encoding that into the vectors. The graph vector models, they also are using the structure of the graph to create these embeddings. So like, where this node, how this node connects to other things. As well as like, it has sort of like, it's similar with like BERT or Word2Vec. It has sort of this stand-in task of like trying to predict a missing word or a context from the word or what have you. Now the graph embeddings are more like static links. It's more like Word2Vec because it doesn't change, because we don't really have a equivalent of like different sentences. And yeah, we were able to do that, and we were able to use it for these same embeddings, use it for a collection of other tasks. There's one a work of research that we did. The paper hasn't come out yet. I'm not sure where that sits, but where we did the same thing for biomarker prediction.
That's right.
So this is like where we're trying to understand how certain genetic sequence variants affect the therapeutic outcome of certain drugs. So we were predicting this relationship, and we found that we could actually, using this knowledge graph, which is based off of like Wikidata and PubMed and some other data sets, we can actually predict these biomarkers, which is like a very specific task. This sort of lends its idea to this notion of foundational model. Plus, because what we did is we would train a local model. We had this global graph, and then we train a local model on a specific task of this relationship. And this is very similar to an LLM's a foundational model, and then supervised fine-tuning or similar refinement techniques for learning specific tasks.
Right. And this is the two-step thing that really we found like a lot of power in, which is like you've got your universe of entities and relationships, and if you're able to build a knowledge graph and train a network embedding model, then you, as Alex pointed out, you get over the cold start problem. Like enough about the domain, and so that becomes your sort of foundational model. And then once you have that, then you can take the results of those as a starting point, like using link prediction and other techniques. And then you can sort of fine tune that to your task specific model, which now you don't need as much data. And so, the data requirements for your second level model that's specific to the task becomes much, much less compared to how much data you would need to train the overall foundational model and the graph itself. And similar to the LLM's story, the bigger the graph, the better and the more predictive power that those embeddings have. And so we sort of did that effectively in multiple use cases, and we were able to demonstrate this using this sort of approach. yeah, and then we worked with, like providers like, Roche and, others. And then the whole LLM thing happened, and then we were trying to see how we can merge the power of the LLMs, use that as a almost like an interface into this knowledge graph. And then we built tooling and like, hey, how do we sort of query the graph and, use the LLM to sort of, power some of these things as well. But the underlying foundational network model was still, was what's the power behind all of this.
And that sort of I guess leaves us at the last project we worked on before this acquisition, which was Pythia, which is where we are trying to combine these two sort of techniques, which is with Pythia, the idea is like, oh, we're going to use LLMs to process, so we wanted to examine LLMs as well. So we use the LLMs then to extract data, even though you can use non-LLM techniques, to extract claims that could like fit in a knowledge graph. And we want to evaluate whether those are accurate and whether they're actually supported by the documents that were used in the generation. So this is something for like testing automatic summarization, testing RAG, RAG-based Q&A.
That's right.
Yeah, and that's sort of like
it's a whirlwind, recap of what last almost 15 years, at least definitely in the last 8 years of Wisecube's existence, and we're pretty happy that we're part of the Jon Snow family now, and we're hoping we can take all of these learnings and all of these technologies and innovations we've done over the years, and join it with some of Jon Snow's really cool tech, some of which was built by Alex yourself, like Spark NLP. You're the original sort of author. You've written a book on it, so it's sort of yes, and it's a homecoming for you, and in some ways for me as well. So we're pretty excited to see what the next stage of our journey in NLP and AI and machine learning holds for all of us. Any last thoughts, Alex, in terms of at least wrapping up this episode?
It's been sort of like this, a really like amazing like journey, because I've been with Wisecube for like 6 years. Ever since I joined, I had this like sort of like really bad itch for wanting to work on some like really greenfield stuff. Like, hey, let's just try something new, and we're going to go from 0 to 60. We're going to try to figure out how to do it, and got to do that a lot over the last 6 years. I look forward to now to like seeing where this, the work we've done and the other stuff like Jon Snow Labs, where that goes from here. Yeah,
I'm excited. Yeah, I think it's going to be great. Jon Snow does a lot of healthcare stuff, but they also have other cool stuff in the works. So so pretty excited, and hopefully we'll do a part 2 of this in a few years, and then try to see where we go from here. But hopefully this has been informational, and in terms of at least sharing some of the history of the NLP and search and these technologies, but also some of our personal anecdotes along the way. Thank you for listening, and keep your comments and questions coming. So without you, this sort of inspires us to do more stuff. So thanks everyone. And
the podcast is continuing, just to make sure everyone knows. The podcast is continuing.
Yes, podcast will continue. Yes, the show must go on. Thanks everyone. See you next time.